and a good day to everyone. Assalamualaikum warahmatullahi wabarakatuh. And I hope you are doing fine despite the fasting month. So we proceed with the last part of thermodynamic property relations. So which is the enthalpy changes. Okay, last time we discussed on the internal energy changes, which is delta U, and this is H. And consider the enthalpy to be a function of T and P, whereby H equals to H to the function of T and P, and take its total differential. So it can be like this, in this form. And using the definition of Cp again, like we previously discussed for internal energy changes. So we have dH equals to Cp dt plus differential H per P to dP. And consider again the entropy to be a function of T and P. So this one is enthalpy and this one is entropy. So we have the same form but this different connotation and different terms, which is S to the function of T and P. S is the entropy, yeah? Okay, S is entropy. So we change the S to H. We substitute this H to S. Okay, and take its total differential to be arranged in this form according to 12.3.2, and substituting this into the TdS relation, whereby dH equals to ds plus VdP, give this dH equals to, according to 12.3.3. And then equating the coefficient of dt and dP in equation 12.3.1 and 12.3.1 and 12.3.3. So we obtain this 12.3.4. And using the fourth Maxwell relation, we have another relation as listed here. And substituting this into equation 12.3.1. So we have, so this one we substitute this term into this one into that one, this one into this point. So we have dH in which can be represented in 12.3.5, whereby this is the delta H general relations, and the change in enthalpy of a simple compressible system associated with the change of state from T1 P1 to T2 P2 is determined by the integration H2 minus H1. And then we integrate it, we can get, so we have to integrate the Cp over dt and V minus T and differential of Vt and over dP as listed in 12.3.6. And the other case can easily be determined by using the definition of enthalpy, whereby H equals to U plus PV. Okay, so this one, it can be, if let's say you want to identify H2 minus H1, so it can be also derived through and calculated through this definition, and it can be equals to this one. And the entropy changes, the first relation is obtained by replacing the first partial derivative in its total differential ds equation 12.2.6 by equation 12.2.8, and the second partial derivative by third Maxwell relation, which is 12.18, yielding ds as listed in 12.3.8, and S2 minus S1 equals to in 12.3.9. And the second relation is obtained by replacing the first partial derivative in the total differential of ds by 12.34, and the second partial derivative by the fourth Maxwell relation, yielding ds equals to Cp per T dt as listed in 12.40. And thus we get letter S, general relation, as listed in 1241, which is S2 minus S1, Cp per T over dt, and differential of Vt over dP. And either relation can be used to determine the entropy change. So it can be 1239 and it can be 1241. Most importantly, it has to depend whether you have data of CV or CP. Right? And the proper choice depends on the available data. Okay, we have another group. We have another task, because basically, if you still remember, there is some marks for the poster. So for each task, require to I will require to I will require you to prepare in the form of posters. So it will be much convenient to calculate in terms of poster, and then we can accumulate it and make it average for each poster in the final one. And please prepare the interactive notes in the form of poster. On how you want to understand the equation of state so properly. So it can be any tips and how you want to remember, and any formula that you want to really, or maybe how you want to link from one equation of state to another equation of state until to this entropy change point. Okay. Okay, for this one, you can submit on week. Week. This is week. Okay, this is okay. Sorry, week 8. Okay, you can submit on week 8. Right, no problem. You can submit on week 8, and this time around, I want you to. This time for this poster, I want you to post on link. Because I believe that some groups are really clever to get more interaction. So basically, this is how you want to get use of the link itself, especially because it might be an useful tool, especially if you want to get a job later on. So I would suggest that it is good for you to get familiarized with the with this with the platform, so it will be much convenient for you when you are about to graduate, because you are now in second year. So it's not that long. I think another 2 years, and then after that you have to graduate. And I want you at least to get the hands on how you're going to get prepared to get hired. So it's best for you to display your understanding on chemical engineering, because we never know, sometimes, or maybe at one point, that people can observe us. So this is one of the way to get more exposure and interaction from other people. Okay, so that is the one of the reason I insist for you to use link. Okay, so we have the example here. Determine the change in the enthalpy of carbon dioxide (CO2) in kilogram per kilogram as it undergoes a change of state from 100 kilopascal and 12 degrees C to 600 kilopascal and 300 degrees C, using the equation of state PV minus A equals to RT, where A equals to 0.01 meter cube per kilogram, and compare the result to the value obtained by using the ideal gas equation of state. So we have the equation 1235 dH equals to Cp dt, and assumption the constant specific heats for CO2 can be used. So for the properties, For the average T is, you can take 433 Kelvin, and the CP will be 0.965 kilojoule per kilogram Kelvin. And the analysis is, we solve the equation of state for volume to give us the value as below. And as we substitute this value, we can get Cp dt plus ADT ADP, and we integrate the result between the two states. So we have and then we can just substitute all the data given here. We have all the pressure and the temperatures, and we can just substitute. So we get 275.2 kilojoule per Kelvin, and for an ideal gas, so it should be dH CPDT only, which when integrated give this value 0.965, the same value for CP, and we just times the difference to the temperature difference for T2 and T1, 120. Okay, actually it can be that way because it is a differential, right? But if it is in Kelvin, or you have only one data, so it should be converted to Kelvin. So for this one, it's not a big deal because we just want to cancel out the Kelvin here. So we can get to 70.2 kilojoule per Kelvin. So basically it can mention here that by using this equation of state, it can give a more specific and a more precise results compared if if you can just use the ideal gas equation of state. Okay, we move on to specific heat CV and CP because most of the time we encountered this like many times, and at low pressures gases behave as ideal gases and their specific heat depends on temperature only, whereby the zero pressure or ideal gas and the specific heats denoted by CVO and CP now, and they are relatively easier to determine. And it is desirable to have some general relation for determining the specific heats at higher temperature, because if at lower temperature it can behave as ideal gas, and at high temperature or lower specific volume from a knowledge of CV or CP and PVT behavior of the substance, and such relations are obtained by applying the test of exactness as listed down here. And the deviation of CP from CV with increasing pressure is determined by integrating 1240. This one is integrated from zero pressure to any pressure along an isothermal path, right? So it is constant temperature. So it should be this is the CV and CV general relations. How you want to relate the CV and the CV. Another desirable general relation involving specific heats which relates to specific heat CP and CV. The advantage of using such a relation whereby we need to determine only one specific heat, usually the CP, and calculate the other one using that relation and the PVT data on the substance, obviously, right? And this development of such a relation starts by equating the 2ds relation and solving for dt as listed here, and by choosing t equals to the function of v and p and differentiating, we get dt as follows, and equating the equation for of either dv or dp of the above two equations give the desired result. So this is the cp and cv general relation number 2, cp minus cp t, right? So basically Okay, so, this CP. Okay, okay. After this, we will go further with this CP and CP. Okay. An alternating form of this relation is obtained by using the cyclic relation, and that we have learned in the first chapter. And substituting the result into equation 1245, it will give Cp minus Cv equals to 1246. And the relation can be expressed in terms of two other thermodynamic properties called the volume expansivity beta and the isothermal compressibility A alpha, which are defined, sorry, this is A, okay, sorry, this is alpha, which are defined as this one, delta equals to 1 over V division Vt over P. And this is volume expansivity, and this is isothermal compressibility, is 1248. And substituting these two relations into equation 1246, we obtain a third generation for Cp and Cv, whereby we can get, we substitute this B and alpha, because we can get from this one, from this point we can get, and we substituting these two relation into 1246, so we obtain a third general relation for Cp minus Cv. Okay, you just have to change this one is B, this one is alpha, this one is beta, so we can get Cp minus Cv equals to V T beta times 2 to the power of 2, sorry, per alpha, which is called as the Mayer relation. So this is CP-CV general relation number 3. Okay, from Mayer relations here, we can get that the conclusion from the Mayer relation, the right hand side of the equation is always greater than or equal to 0. Therefore, we conclude that Cp, it should be larger or equal to Cv, right? So it makes sense here if it is 0 or equal. And the differences between Cp and Cv approaches 0 as the absolute T approaches 0. And last one is the two specific heats are identical for truly incompressible substances since V constant. The difference between the two specific heats is very small and is usually disregarded for substances that are nearly incompressible such as liquids and solids. Okay, so this is the visual representative of the substance. If let's say the substance with a large beta, so it's going to be like this. And if let's say a substance with a small beta, it's going to be represented by this visual representative, which equals to the Cv and Cb. And the volume expansivity, also called the coefficient of volumetric expansion, is a measure of the change in volume with temperature at constant P, as denoted from this A and B. So this also the real life example, because we can see that the internal energies and specifics of ideal gases and incompressible substances depend on temperature only, right? So that's why we can see it is highly dependent on the temperature U, Cv, Cp, U and C also. Okay, so we have delta H, delta U, and delta S of the real gases. Just now we have the gases, so this is the real gases. And gases at low pressure behave as ideal gases, as I mentioned previously, and obey the relation PV equals to RT. And the properties of ideal gases are relatively easy to evaluate since the properties U, H, CV, Cp depend on the temperature only. At high pressure, however, gases deviate considerably from ideal gas behavior, it becomes necessary to account for this deviation and to evaluate the changes in the enthalpy, internal energy, and entropy of non-ideal or real gases using the general relation for du, dh, and ds developed earlier. So enthalpy changes of real gases. The enthalpy of a real gas in general depends on pressure and T, like unlike previously, whereby for the ideal gas it depends more highly on the temperature. And the enthalpy change of a real gas during a process can be evaluated from the general relation for dH, whereby H is H minus equal minus H2 minus H1 equals to the term follows. And for an isothermal process, dt equals to 0, and the first term vanishes because this one is 0. And for a constant pressure process, dp equals 0, and the second term vanishes. So because it is highly dependent on pressure and temperature. And this is the alternative process path to evaluate the enthalpy changes of the real gases. So this is how you graphically represent the enthalpy change of real gases. And using a superscript asterisk to denote an ideal gas state, we can express the enthalpy change of a real gas using during the process 1 and 2 S here. So this is the ideal gas state, yeah. So we just do the rearrangement here, so we can get this one, and as follows here. And the enthalpy departure refers to the difference between H and H asterisk is, and it represents the variation of the enthalpy of a gas with pressure at a fixed temperature. And also can use the relation PV equals to ZRT, whereby Z is the compressibility factor and whereby it is substituting. So you get the enthalpy departure between the ideal gas and the real gas. And T equals to TCR TR and P equals to PCR PR. So this is the enthalpy departure factor, the Z here. And the values of ZH are presented in graphical form as a function of PR, or reduced pressure, and TR, or reduced temperature, in the generalized enthalpy departure chart. ZH is used to determine the deviation of the enthalpy of a gas at a given P and T from the enthalpy of an ideal gas at the same temperature. And this one is for a real gas during process 1 and 2. So this 1 and 2, 1 and 2 refers to from point 1 and point 2, and taken from the ideal gas table, so we can get H2 minus H1 of the ideal gas. Okay, all right. Next one is the internal energy changes of real gases, and using the definition, H equals to U plus PV and U plus ZRUT, and U minus 2 U2 minus U1 equals to H2 minus H1, and so accordingly, so we can just convert it from the available relation. And next one is the entropy changes of real gas, general relation for ds as follows. And using the approach in the figure, so we have, as we implement here, H2 S2. So this is B, yeah, S2 minus SB. And during the isothermal process, so these are the point whereby this one SP minus SO. Okay, this is as SP. Okay, this is SP minus SO, and SO minus SP, whereby it is at the constant temperature. So it should be this point, the constant temperature okay, if let's say you want to do this one, S2 minus S1, S2 minus S1, so you can get S2 minus SB plus SB minus S2, so plus S2 minus S1 plus S1 minus SA and SA minus S1. So this is basically an alternative process path to evaluate the entropy changes of real gases during process 1 to 2 by using the available data that we have. Okay, and during the isothermal process, so it will be um, it will be summarized as follows here, and then we can get the SP minus SP. Sorry, so we can sorry. Sorry. And how this is how you want to derive the equations, and after that, after using the same departure factor like this one, this is enthalpy departure factor, so this is the entropy departure factor, so which equals to Z, right? Because this one also Z PV equals to RT, the same one is the same correlation, but it's just the same, it's just a different form. So it will be translated into the entropy departure factor as follows, whereby this is the entropy departure. And the values of Zs are presented in graphical form as a function of reduced pressure and reduced temperature in the generalized entropy departure chart. And Zs is used to determine the deviation of entropy of a gas at a given P and temperature from the entropy of an ideal gas at the same pressure and temperature. And this is the relation for a real gas during a process 1 and 2. And this is from the ideal gas relation S2 minus S1. Okay, so that's all for chapter 2. Um, Most probably we will have a short quiz to not short quiz, like short exercise, so that we can evaluate and we can recap back our understanding on the chapter 2. All right, thank you for your time, and don't forget to submit your assignment on not your poster on week 8. All right, all the best.